And so, yeah, just tell me if anyone wants to speak afterwards, or if you have some other speakers for next time. I talked to Derek and he said he might want to talk about Hamilton-Jacobi equation. So if you don't have anyone, he can speak. Today, Klaus continuing his talk. I hope everything is okay.
Do you think the sound is okay?
Yeah, I mean, it registers, so it should be fine.
Good.
Okay, so please,
Good. Okay, so this is the second part of low particle production in one dimension. And I maybe clarify from last time because I got the impression that some of you thought that I claimed that there's no particle production in 1+1 dimension. That's not what I was saying. We were looking at a model with many coupling constants, and then infinite coupling constants, and then we set these coupling constants to some very specific way, such that all the amplitude vanish, and there will be no particle production. But that is a very special situation. That's not linear. So you shouldn't take this literally. It would be a very special case that we are looking at. This is what we try to do. So I remind you that the model in 1+1 dimension was given by Lagrange density. So I'll just briefly remind what we did last time. You should have forgotten in 8 days. Or if there's somebody new. And so we'll be looking at this Lagrangian, where the potential density is given by the mass term squared phi squared plus sum of n bigger than 3 lambda n over n factorial n, and we found that the interaction could the coupling constant, they had dimension of n squared gn. This is dimensionless, and often we will always put speed multiplied to 1, but depending on whether we have to talk about loops, then h bar could be different from 1, but usually it's 1. And also it becomes really tedious to work with this mass parameter. So often we will also scale that to 1. And that means that we especially are considering massive theory. And then the next thing we did was we looked at endpoint amplitudes, where we draw like this, where we had some n, we have some particles coming in and out, n with some momentum, k1, k2, all the way up to kn. And we ordered so it's outgoing here. So we have a total momentum conservation. This is B0, and then and the amplitude. Yeah, I didn't really explain much what it was, other than I gave a prescription. So we had to do some Feynman diagrams and sum over different Feynman diagrams. And the type of Feynman diagrams we talk about are so-called connected tree, and they compensated, which means that we don't take the external edge into account, and function. So and then it was very useful to go to light cone coordinates. So instead of using energy and momentum, so we have energy is 0, and momentum K1 in 2 dimensions, then we use the plus minus micron coordinates. That's not 45 dimensions, the whole is close enough. And then there would be a mass shell condition, which is of course a mass hyperbola. We have something like this with M minus M. And in light coordinates, we got that K plus and K minus was given by some square root of 2 A and 1 over A, where this was a free parameter A. And we were interested in the analytic structure of this. So therefore, even though physically A belonged to the real axis, we will now expand and think of A as a complex variable, maybe to from 0. We have the other one here. So that was what we looked at last time. And furthermore, maybe I should also say that the way we found these Feynman diagram rules was that we had some Feynman rules. And that was basically one for the lines propagated in momentum space. It was given by 1 over k squared plus m squared I epsilon. And this regular station I epsilon we will not talk so much about. And there was for every time we had an inverses, then we had to put in a coupling constant lambda n, basically. So that's and then we could build up the Feynman diagrams, the tree diagrams in this way, and in the k squared, if we take into account the metric of light cone, there's a -2. There's a -2 k plus k minus in this dimension. Okay. Then last time we spent a lot of time in calculating these amplitudes. So the first one was very simple. It was just one diagram. We saw that A3 was different from 0, and we also improved a formula function. And we saw that that's also different from 0, with a sum of 4 diagrams. And then we spent a lot of time with the next two. We saw that the A5 to be constant. Then you have to demand. There's only 2 possibilities: either G3 should be 0, or G4 should be equal to, I think it was 3G3 squared. So that was a condition to get rid of poles of the A5. Then you only have 2 solutions, and then we further saw that when we look at a 5 point and above, then we could put it equal to 0. But then the lambda n would be uniquely fixed. But unknown. And maybe let me remind you a little bit what was going on here. So the most important part of the argument was given by something called factorization, where you can commit yourself that for 3 amplitudes, when you have K1, K2, up to Kn, over Kn, and you look at a certain channel where K1 plus up to Kr squared plus N squared happen to go 0 to 0, which is precisely a propagator where we have this external momentum flowing through. Then it turns out that the amplitude factorizes into 2 sub amplitudes, and then a propagator, which is precisely this propagator by K1 plus up to Kr there. We would have, and then obviously you would have here you have K, this would be K2, so here you have Kr, you would have K2, you have K1, and here you would have Kr plus 1, and so on, and this last one would be N. So this, obviously, if you count the number of legs, this would be Kr plus 1, and this would be N minus R plus 1, because there's one extra leg, internal leg. And so the point with this factorization was that in the limit where external legs satisfy such condition, then all the diagrams which contain this propagator, which becomes very, very big in this limit, dominates, and we can, in this limit, they will dominate all overall diagrams, and it turns out that the dominant diagrams is these diagrams. That's factorization. And this was very powerful because we could now from the fact that we know that An is a rational function of the momentum, then and from the fact that proof symmetry was scale symmetry, then we know that the order of this rational polynomial, so there's a polynomial in momentum upstairs and downstairs, and that order had to be the same because of scale symmetry. And that led to the very convenient or useful statement that if there's no pole, if An has no poles, then An must be a constant. And we used that all the time last time. And the next step was that since when we look at all the diagrams, they contribute to An, then the simplest diagram then is decided just for the n quantitative function, then that would be just lambda n diagram. I mean, where you use the n vertex, and that diagram has the value minus lambda n. So the point, and then there will be other distributions. So if we know that An is constant, then we can always shift the value of lambda n such that this becomes 0. Make sense? I see R is nodding. So so that means that we can keep An to 0, and that was exactly what I meant by that lambda n is uniquely determined but unknown. And so today, the plan today is we would like to determine lambda n, all the lambda n's that we know exist, but we just don't know the value of it. Okay. So and we will, so for that we will use 2 tricks. Okay, are there any questions to? So Stanislav is happy. Good. Giacomo. Good. All right. So that was how far it got last time. Oh, maybe we should just repeat, because it's so short. Maybe we should just repeat the argument for why how we got I mean this factorization argument. So the point is, we spent a lot of time of explaining why A5 and A6 are zero. But then we will then use induction from A7. So let's assume that we have proven already that all the diagrams between from 5 and up to n are zero. And then we will now look at an plus 1. And then we're going to split that. And then we want to ask, we already know it's a rational function. So we want to know if it has any poles. And so then we ask, does it have a pole associated with it has to be associated with some quantitative going to become large, or denominator going to 0. So then we know that from factorization that it would be something like a R, and then I guess it would be a R n minus R plus 3 or something like that. That would be the structure. And we know that so the point is that so we're asking, is there a pole here? And so we know that n we already know this for let me see, we know that n plus 1 is bigger than 7, or because we know we have already checked 5 and 6 explicitly. So we can assume that n plus 1 is bigger than 7. And therefore we know that the sum of these two guys, because there's two more, because the sum of these two must be bigger than 9. And therefore we know that one of them must be bigger than 5. Right? And then the point is that both of them must be I mean they must be within that what we already know is 0. Except some of them could be a 3 and a 4, which is non-zero. So we have to make sure that at least one of them is a 5 or a 5. But then we can then use this answer to prove that this is actually 0 and it doesn't have any poles, and therefore we can then shift lambda n so it becomes 0. So that's the idea. Does that make sense?
Well, so you said that A3 and A4 are
not 0. Yeah. We cannot touch those.
And you suppose that 5 and is 0, and
Yeah. I think it was like I'm not so clear why this 5 appeared, but that's essential because we cannot touch a unit 4. Okay, so that was what we did last time, and then we will need 2 tricks to be able to determine the lambda n's. And the first trick is that we know that these amplitudes are constant, so they don't depend on the momentum. And so we will do a trick. We will simply use a particular set of momenta in kinematic space, which is most easy to calculate. So we will take a certain limit, and that limit goes under the name multi-racking limit. So now we just need to evaluate the Feynman diagrams for one a typical set of momenta, and now we will pick these momenta in a smart way. And what we're going to do is we're going to take a one parameter family. So we're going to say A2 is equal to, so I'm looking at AN here. Next. And you know, we talked about last time that AN on shell and off shell would depend on 2n momentum variables because we're in 2 dimensions. And on shell we get just n because so the n variables, and then there's momentum conservation that will take away 2 extra. So there's n minus 2 independent variables. And so A2, we start with A2 and end with AN minus 1. So we will not A1 and AN, we will not do anything. So we just take this one and then we say, okay, let this be equal to x to the 0th power, A3 equal to x to the first, and AI equal to x to the I minus 2, and AN become x to the n minus 3, where x is some big number. So this, and then we will drive x to infinity. So that will be the idea. So you should think of like we have come the momentum. So our particles will the A2 particle will have x0, so that was 1 in this unit, and then A3 will be very fast compared to, and A so on will be faster and faster. Make sense? And so the next thing we're going to do is what about A1 and AN? And there we're going to use momentum conservation. So we know that for momentum conservation, we know that AN plus A1 plus AN and A1 minus first, that the K plus and K minus component, they have to satisfy. So then we call the sum equal to, they have to be minus I equal 2 to n minus 1 AI. And this has to be equal to minus I equal 2 n minus 1 AI minus 1. Does that make sense?
You said that A is a complex number.
Yes.
Now you're saying that it's a
if you
real
want
number or just the real part is.
The x. Yeah. So the general A's are complex numbers different from 0. And when you want to go to the physical regime, then you make them real. And actually, they will be real in this case because I take A to be real and large. So yeah, so they're not complex anymore, actually.
Can people like complex just saying that the real part is increasing very fast?
It's not necessary. I guess you could do that if you want, but if this would be enough to just look at the real. So we have this, and then I can now use the Reggie limit, so I get something like that. This is equal to minus I equal 2 to n minus 1 x I equals 2, and this one will be minus sum over I equal 2 to n minus 1 x. I guess it's 2 minus 5 in this case. Something like that, and then of course from here I get that this is going to be O. This is going to be minus x n minus 3 1 plus order x minus 1. So the point is basically that if this number here will be determined by the biggest x power, which is from the n-1 particle, which has the biggest one, and then will be n-3 here. And then there will be some leading contributions from the other particles. And from this one, then this is inverse power. So the dominant one will actually be the first one, and then there will be sub-leading contributions like this. Does that make sense? Okay, so now you see you have two equations and two unknowns for the last two momentum variables. And that's two equations, two unknowns. You can easily realize this is actually a second order equation, algebraic second order equation. We're not going to do that. You will believe that I can do that. And also you see it's complete symmetric. So you see that the solutions will just be that you switch what you call A1 and AN. So now I'm gonna show you the solution, and you can see that that's probably that will satisfy it. So I'm saying that A1 is of this form, and AN. We will only need this to know that it's on this form xn minus p plus sub-leading relations by something like 1 plus sub-leading to this. And now you see that I have chosen, there's two branches, and I have chosen that I will always demand A1 to be -1, the one which is -1 branch, and AN to be the big one here. So you see AN is very close to AN -1, and A1 is very close to A2. They're just opposite sign. Make sense? I see Mikael have joined us. Mikael, can you hear us?
Yes.
Good. Right. So that's the multi-related, and so now we would like to calculate the internal propagators in the multi-related limit. As you can guess, the point with this multi-related limit is that most internal propagators will vanish. And there will only be very few that actually survives in that limit. That's the idea. So we don't have to sum so many diagrams. Let's look at a generic internal propagator. So let's call this set I, and this set index set J. So the point is, I will be index from I1 by R. So this would be an R propagator, where R stands for how many internal momenta, external momenta flows through. So here, let's say that we have on one side these indices, and on the other side we have these indices, Jn minus R. And so the point is now that it's only interesting to have R to be between 2 and n-2, because we need at least 2 legs on each side, because else it will not be an internal propagator. And the other thing I'm trying to convince you is that we can assume that I1 is less than I2, and so on. And we can also assume that J1 is less than Jn. And we can also assume that I1 is 1. So that would be, else we just flip I and J. So another way, I'm just playing with the fact that I1 and J should be the full set of indices from 1 to n, and I and J should be the indices. And it's ordered like that. So we will now try to calculate what would be the list propagator with these indices, where we of course now take the multi-rated limit. So let's do that. So so we're looking at m squared. I'm getting fast and tired of writing m, so I will often put m to be 1, but let's make it more clear if people write it explicitly. So remember we have this minus 2 sum over the k plus of belonging to I, and then sum over k minus I here plus n squared. So this is our propagator, right? And now we want to rewrite that with the help of the A variables. So there was some, I feel that maybe you have it on the blackboard. I apparently don't, but I hope you believe me if I say that this is the same. There was a square root of 2 that goes away, and so it becomes A, the K plus becomes basically AI. I belong to I, and for the K minus, I will actually pick the J set instead, but I know from conventional conservation that that's the same as putting a minus, and that takes away that minus here. So therefore I can write J belongs to J A J minus first, which is the minus component. Does that make sense? I see Stanislav is nodding. So now we insert the this Reggie multi-Reggie limit, and so this will become something like 1 over I think it's x are minus 2, 1 plus O of x minus first, x 2 minus a1 plus 1. So this is a little bit wrong, but this apart from some special cases, this is actually basically what's going on. So the point is basically that from the index set I, here we have we're most interested in the most dominant of these AI, and we know that this is increasing. So we know that the R1 would be the dominant one, and the other one will just be some dominant contribution. So it would be this here.
So there's a point that's A1 and A10 are both points.
Exactly. Yeah. So then this is where I have been stopping. Let me finish the generic argument, and then let's go to the special case that Linus is pointing out. So
A1 is minus 1.
what?
You chose A1 to be minus 1. So
A1, but I cannot choose it to be exactly minus 1. I have to, when you do the second order equation, then you realize there's some sub-leading contributions. But I didn't specify what they are, because I don't need it. So notice that all the other A2 to AN, that's some power of X. But the other one is from solving a second order equation, and it's a little bit more ugly than these two. So the point is exactly as Linus noticed, is that this argument only works if 2 is less than I is less than N. In this case, then what I said is correct. But there are some special cases. For instance, if IN is I is N. So the point is that if R is N, then we don't get, then the scaling is a little different. Because it doesn't, I mean, if this should hold, then it should be a, yeah, so this formula would hold if I should write an equal to hn minus 2 and a1 equal to h minus 1. That would be the pattern here, but this is wrong because that violates the momentum property. So I have these two anomalous objects here, which destroys my beautiful formula here, my argument here. So I had to pick that out and do that by itself. Does that make sense? So, wait,
I is,
yeah.
I think that there's no propagator, that it's just, chasing at the set and do everything overlap.
No, it could be that, for instance, it could be 1 and n here.
Oh, yeah.
And
Yeah.
so I never said that J1 should be bigger than
Yeah.
yeah. So the point is that if R is n, then you can convince yourself that I can get away with the same expression if I include an O x minus first here. It becomes a little bit smaller, but it could actually become more small because it could be that, that there's more constellation going on. So that's
Sorry, included where? Included below.
here.
Okay.
And then there's another case if R is 2. Then we are in a very special situation. If R is 2, then there's actually only 2 elements here, and it's 1 and 2. And 1 and 2 partially cancel each other if you look at the formula, because a2 is 1 and a1 is minus 1. So so the leading terms cancel each other, and in that case you can actually convince yourself that instead of well, this is actually 0, and it actually also works with this guy here. Oh, sorry, it's not 0. This is 2. Now I confused myself. It is not 2. So, oh yeah, so it is actually 0. So actually it works if this factor here is all x minus 1. Like if I write that instead, then this case would also be covered. Okay, so and then you can convince yourself that if we are in and actually in all cases. In all cases, it turns out that this, when x going to infinite, it becomes 0 if I is bigger than k1, and it becomes 1 if I is less than k1. In all cases. So you see here, let's think of this one. So if R is bigger than J1, then you see that this will dominate over 1, and we will get 0. And in the other way, then this would vanish, and the 1 will dominate, and we get 1. And you can, I think you can go through the other cases, and you can realize that this does not destroy this pattern. And this is beautiful because you see now there's actually only very few propagators that that now can contribute. So, so the conclusion is that the only one which survives is if we are talking about we have all, then on one side we have the eyes are this and this is are not in so they have to be ordered. Does that make sense? That if this is the case, then we get one and all the rest they have zero. It's very nice. So the point is that when you look at the propagate, internal propagate in this multi-rate limit, then all the labeling on one side should be smaller than on the other side. If there's some kind of mixing there, then the propagator wins. So you can imagine that's very powerful. There's not many propagators that survive this limit. So so that's the first trick. The next trick is what I call a vertex expansion. And this is a little bit the same as so for instance, okay, now I mentioned something that really doesn't have anything to do with this. I just want to give you another example of an expansion where you expand, for instance, the determinant with respect to rows or columns. And I think this is called the class expansion. So the point is that you expand and you get the determinant in the sum of determinant 1 degree less. We will do the same here. So the idea is that we take from an AN diagram and we assume that we have what's the word, a distinguished leg here on which we'll call 1. Yes, this I would call a distinguished leg, and then we ask the question: how does this diagram look like? We want to expand this diagram according to what happens next for this leg's point of view. And obviously, the first thing that this leg meets is a vertex, right? So this is why I call it vertex expansion. So it will be equal to a sum of vertices 1 to lambda r, so r going from 3 to n, like that, and then there will be legs out of that vertex here. And then that can happen 2 things. Either the legs are internal or they're external. So it turns out that you just that there is a vertex expansion. Say you have to sum over all possibilities. So there will be some internal ones, and then there will be an A of whatever degree is needed for that, and then there will be internal one, and then there might be an external one, and external, and you have to sum over all possibilities. And so this vertex expansion, I've actually never seen it in the textbook. I've only seen it in highly technical applications. For instance, I think in young use, I've seen something called Bellman's G relation. And this is the closest I can give a name to. I guess it must be well known to people. Here, I should also stress that this only works for 3 amplitudes. So, this is the expansion we're going to use. So, in more detail, there will be we have some more various possibilities. So the first possibility is that all the legs are external. So that will be the first contribution. It will of course be lambda. So the first one will be 1, and then the lambda n, and then just external legs. So this there will be, let me call that 0. There's 0 internal lines here. That's the first thing that can happen. The next thing that can happen is that we have 1 internal line. So it will be something like 1, and then lambda bar, and then 2 up to r minus 1, and then 1 internal line. So here we have external lines, and then we have here we have an A, and I guess this must be, I wrote that to be n plus 2 minus r n, like that, and then the next contribution would be where we have 2, for instance. So then 1, and then lambda, maybe that's not come back, and then here, and then we have 2 an, and then we have an, like that, or like a something, and like that here. So, these 2 are internal. And the point is now that the n can sit, where is the last? It could sit here, it could sit here, and it could sit here. And the point is now that wherever it sits, does it sit here, or does it sit here, or does it sit here? Wherever we put this, then you can convince yourself that one of these 2 internal lines will not satisfy the multi-region limit requirement. For instance, if you say that n sits here, then this could potentially be that all the 1 up to r sits here and all the bigger ones sits here, so it survives. But then n would not sit here. And then from this point of view, 1 and n would sit on the same side on that propagator, and therefore we cannot, they will not be ordered. Does that make sense? So,
So was the problem that n sitting on the top, right?
so let's assume this is there.
Yeah.
If you sit there, of course it's symmetric, this and this is symmetric. So let's assume this is here, for instance.
Well, if you want to order it, it's not symmetric.
Well, there's no meaning to order. I mean, other than I'm going. So let's take into it. Then this could potentially be okay if all of these guys are bigger than all of these guys. But if we assume that and this survive, then this guy would have 1 and n on the same side from this perspective. So this can definitely not survive. And so on. We can also put n here, then both of them cannot survive. And so on. So we see that multiple internal legs in this vertical expansion cannot contribute in this method. This is perfect because then we only have to consider the 0th and the first term. But there's more good news because many of these ANs, they're 0. So So we get. There's in fact.
Well, we
Only,
probably will use that argument also to rule out this second.
yeah, this one right down there.
Yeah,
Yeah.
one of the eight will be 0.
Yeah, you're absolutely right. So, yeah, and higher ones, the 3 goes into 1 goes also. So. Maybe, I guess it's time to move this one instead. Yeah, so what can survive at the one, so the one, how many of these can survive? So the point is there's actually only 2, because then we know that the A have to be A3 or A4, because all the other A's are 0. So so that means that we only get 2 possibilities. One is lambda n minus 1, and then here, and then we get an A3, and then we get here an n minus 1. It has to be like that. This is the distinguished here, so we have 2 and up to n minus 2, like that. That's one possibility, and the other possibility is plus distinguished lambda n minus 2. And then an internal one, and then we have A4, and then we have n minus 1, and n minus 2, n minus 3, 2. Does that make sense? This is the only 2 diagrams from the one. So we actually have 3 diagrams. We have the one from 0, and then we have 2 from this guy. And that's all. And we also furthermore know that this AN is 0. Because we constructed it to be 0. That's our instance. Make sense? So, so therefore, I get that 0 is equal to AN is equal to, and now I put n to be 1. So the 0 order contribution gives you a minus Gn or lambda n, and the next I get here, I get from the here I get Gn minus 1, and then I get A3 of n minus 2, n minus 1, n, and then I get minus Gn. I guess it should be minus 2 here. And then A4 of n minus 3, n minus 2, n minus 1, n. So that's the formula. And we already know that this here is minus G3. This one.
I'm not sure where you wrote n minus 2, n minus 1, and the n minus 2, that should correspond to the internal. Minus 2. It doesn't matter because it's a constant.
Oh, yeah. Oh, sorry.
There's n minus 1 and internal.
It is also this.
Yeah, it should be the internal.
Yeah. Yes, you're right. Yeah, it's something. Yeah, thank you. To have that, but I guess this makes sense because we're multiplying this with that, and then we have the propagator, which is 1, because it's the surviving propagator. And then we have this guy here. And then the minus, no more to multiply with minus, this is in some convention. Yeah. So then from here, well, the A4 we have to think a little bit more hard about, because remember that we have 4 diagrams that contribute to A4. So let me write those 4 diagrams. So write them here. So one was, of course, the lambda form of G4. And then there will be, let's attach to it's attached to this here. That would be one diagram. So yeah, so we're talking about this here. The other one, then there was some diagrams in ST and U channels. So we would get something like this. So this would be n minus 2, n minus 1, n, and then there will be here the same one, like that. So that's another contribution that contribute this. And then there's 2 more, the T and U channel. So there will be this one. Well, I can actually get all the same and then just commute the legs. So that would be, so this equation would be n minus 1, n minus 2, n, and this would be n minus 2, n minus 1. We have 1 here. And then you can you see that this here satisfies the multiplication limits. This is 1, but this does not satisfy. This is actually 0, and this one does not satisfy. This is 0. So we only get a contribution from, should we call it S channel, and then the 4 contribution here. So these are 0. So altogether, we get that 0 is equal to minus Gn plus Gn minus 1 G3 minus Gn minus 2 minus G4 plus G3 squared. Like that. So this is for the 4 interaction, this is for the S channel. Does that make sense? So this is really nice because now we have a recursion relation that can tell us how we can get Gn from the 2 previous Gn. And we already know the beginning. We know G3 and G4. We assume these are fixed, so we can now solve this in a unique fashion. And I'll just give you the result. So if you remember, we had 2 cases. We had either the G3 had to be 0, and we had another case where G4 had to be equal to 3G3 squared. So there's these 2 cases. The first case becomes that Gn had to be equal to 1 plus minus 1n over 2. So this is a way to say it only have to be only even. G4 n part minus 1. You can convince yourself that solves this. And in the other case, you get the Gn have to be equal to 2 to the n plus 2 minus 1 to the n over 6 G3 n minus 2. You get these strange numbers. This one is particularly simple. So if you plug this into our potential, which is long gone, then you get this is equal to G4 cosine. We will call it cosine square root of G4 by -1. So this is the Gordon potential. And the other one is weird. So if we plug that into the potential, then you get this is n squared over 6g3 squared e to the 2g3 pi plus 2e to the minus g3 pi minus 3. And this model is known as the Bullock-Dodge model. We get these two deep potential.
What about Steinborn?
That can be achieved by using a complex rotation on G. I guess it's G4. I think it's minus. It's the Steinborn you get by putting this to be negative.
Yeah.
Yeah. So it's included.
Yeah, it should come out.
Yeah, it's included. Yeah. So if you the point is that if you put G4 to be negative, then this becomes imaginary.
Yeah.
And then put the hyperbolic cosine becomes cosine.
Yeah, that's just because when you
Yeah.
over positive.
Yeah. Yeah, it comes in there. All this works because it's conservative. I mean, you can think of it as complex. Complex constants. Yeah.
So what's like the context for application that the second model of this? It doesn't name, this is to be famous somewhere.
Yeah, well, I mean, it's famous in the sense that these are the two. Well, I should say that here, so you could ask, okay, if you did this in 2 dimensions, okay, I'm sure you want to keep in 2 dimensions, but what could you have done? Yeah, so one we could have talked about derivative problems. We didn't do that. We will not do that. The other thing you can do is you could introduce more fields. And there is a whole there's something called affine total theories, where these are actually examples. The rank 1, these two are the full classification of rank 1 affine total theories. And so there would be if you introduce more fields, then you can adjust them to also have low particle production. They're known as affine total theories. And I mean, this is particularly weird because you notice, I mean, you have different coefficient of that here with the exponential, and also different coefficient here in front of that. And I think I wrote. I mean, I read some papers, but I'm not claiming to really understand what's going on. But I read somewhere that this Bullock-Dodge model can be understood as some kind of reduction from, I think, it's single lace model. So it's some kind of folding of from a higher rank theory, where it's more natural. So, but yeah, it's an interesting topic. There's a huge literature on that. So yeah, so that's more or less, I think, what I wanted to say.
I mean, another reason of the famous is with the interval.
Yeah, that's
The
true.
quantity,
Yeah.
yeah, not at a tree level.
Yeah.
It's not good.
Yeah, I the total point models, I think they are.
Yeah, I mean, it was a sign what this. I don't know how much.
Yeah.
Well, if it's a linear. There are the only integrable, also,
No.
No, it's then only when you want to, I mean, with one field. One
Yeah.
field, and you have to, but you can.
yeah, so you have, like, this is not that you have to prove that you have it.
That's right. But if there are different species, we have only one type of particles.
Yeah. Okay, thanks, speaking. Do you have any questions? Yeah, so if not, then I suggest we take a break next week, and if someone wants to talk, just say to me or Patrick. And if no one wants to talk in 2 weeks, you can have Derek. He said he wanted to talk about something with analogical equation. So I'll talk to him and give you the abstract. And see if you want to come. Okay, thanks.
What about one word?
Yeah, but one of them, I don't know.
There's some result.